Some amounts are simply impossible to pay with these coins. This machine takes only 3 cent or 4 cent coins, and every payment must use just one type. So you can pay 3, 6, 9 or 4, 8, 12 once. What's the fifth amount you could ever pay? You have infinite coins of each denomination, but you can only use one denomination at a time to build an amount, no mixing. The problem asks, among all amounts that can be formed this way, what's the kth smallest one? This one's LeetCode theory 1 and 6, kth smallest amount with single denomination combination. Hey, I'm Kai and welcome back to Fun with Learning Technology. It's rated hard, and once you see the trick, you'll understand why. You get an array of coin values, and you can use as many of each coin as you want. The catch is, you can never combine two different coin types in the same payment. So a payment of 9 could be 3 3s, but never a 6 plus a 3. Across every coin, sorted smallest to largest, we want the kth amount on that list. Let's trace the real example, coins 3, 6, 9 and k equals 3. Coin 3 gives 3, 6, 9, 12. Coin 6 gives 6, 12, 18. Coin 9 gives 9, 18, 27. Merge every one of those lists, sort it, and the amounts are just 3, 6, 9, 12 because 6 and 9 are already multiples of 3. Nothing new sneaks in early. The third smallest amount is 9, which is exactly the answer. Up to 15 coins means we can afford to look at every subset of them, since 2 to the power 15 is only about 32,000. K can be up to 2 billion, so actually generating and sorting amounts one by one is out of the question. And the coins are distinct, so we never waste work on two identical multiple lists. The obvious move is to just generate multiples of every coin, dump them in a set to kill duplicates, sort, and grab the kth one. It works on the small example. But k can be 2 billion, and this builds an actual list of 2 billion numbers first. That's not going to finish in time. 3's multiples, 3, 6, 9, 12, 15. 4's multiples, 4, 8, 12, 16. 12 shows up in both lists. With more coins, this overlap explodes, and every merge has to quietly untangle it. Don't list amounts one by one. Instead, pick a number x. Ask how many valid amounts are at most x. If that count matches k, you found your answer. Picture 2 raffles. 5 people won prize A, 4 people won prize B, but 2 people won both. Add 5 plus 4 and you've counted those 2 winners twice. Same problem here. Count multiples of 3 up to x, x divided by 3. Count multiples of 4 up to x, x divided by 4. But multiples of 12 got counted twice, so subtract multiples of the least common multiple once to fix it. Start with a huge range for x. Pick the midpoint and count valid amounts at most. That midpoint. Too few? Search higher. Too many? Search lower. Keep narrowing until you land on the exact kth smallest amount. This turns the inclusion-exclusion idea straight into code. For every subset size, we look at every combination of that many coins, take their least common multiple, and count how many multiples of that fit under x. Odd size subsets get added, even size ones get subtracted, and that cancels out every double count. Now wire that counting function into a binary search. We start with a range wide enough to guarantee the answer sits inside it, then keep shrinking toward the smallest x where the count is at least k. When low and high meet, that's the answer. Here's the whole thing put together. We import combinations from itertools and LCM from math. Those do the heavy lifting. Inside, count takes a number x and tells us how many amounts up to x are actually makeable. It loops over every possible group size. 1 coin, 2 coins, and so on. And for each size, every combination of coins at that size. For each combination, we take the least common multiple, that's the smallest number every coin in that group can build together. Then we count how many multiples of that LCM fit under x, adding it if the group size is odd, subtracting if it's even. That's inclusion. Exclusion, cancelling out amounts we'd otherwise count more than once. Once count works, the real search is a binary search on the answer itself. Low starts at 1, high starts at the smallest coin times k, since that's always big enough to contain the kth amount. Each step we check the midpoint. If count of mid is at least k, the answer is mid or smaller, so we pull high down, otherwise we push low up. When low and high meet, that's our answer, and we return it. Brute force has to grow a list size by k and by how large the amounts get. This approach never grows a list at all. It takes roughly log of the range steps, and each one just does a small subset count. Coins 3 and 4, looking for the fifth smallest amount. Binary search narrows in on X. Count multiples of 3 plus 4 minus overlap at 12. The answer lands on 9. No brute force list required. Time is roughly 2 to the power of the number of coins for every subset times about 40 binary search steps for the range. Space stays small, just proportional to the number of coins. None of that is specific to coins. Anytime you need the kth item out of a set to use to list, ask how many are at most X and binary search that count instead. Stock is cheap. Let's actually run this. I fed it all 2 of the problem's real examples. No cherry picking plus 3 extra edge cases I picked myself. Let's actually time both on a real 50 element input. Brute force took 1.79 seconds. The optimal version took 185.74 milliseconds. That's a real 9.6x from actually running both just now, not a complexity estimate. Here's one to chew on. When you binary search on the value X, what property does your check function need to have for that search to actually work? Pause here and think it through. Take a second before I give it away. The count of valid amounts up to X has to be monotonically non-decreasing as X grows. Without that, binary search would just be wrong, not just slow. Second one, suppose every coin value shares a common factor, K, like 6, 10 and 14. Does that change the range you binary search over or just how you count? Guess before I answer. Give it a moment. It only changes the counting step. The search bounds stay the same. Because the common factor just scales, which multiples get double counted, not how big the answer can be. We solved LC316 by flipping the question from picking the kth value directly to counting how many payable amounts fall at or below a guess X. Inclusion-Exclusion over subsets of the coins gives an exact count without double counting shared multiples, and binary searching X over that monotonic count function lands on the kth smallest amount. That count runs in O2 to N per check times or lodge for the binary search.